Welcome to our presentation on advanced single equation analysis. Today, we'll embark on a comprehensive journey, exploring the theory behind various advanced econometric techniques and their practical implementation using EViews. We'll delve into topics ranging from volatility modeling to cointegration and the nuances of limited dependent variables. As our guiding motto states, data speaks, and advanced methods ensure we are listening to the right frequency. This means moving beyond standard assumptions to truly uncover the complex relationships within economic data. For example, understanding not just the average effect of a policy, but also its impact on market volatility is crucial for comprehensive risk management. To appreciate the necessity of these advanced methods, let's first examine the limitations of classical assumptions in the face of real-world economic complexities. The classical linear regression model, often estimated with OLS, rests on several key assumptions, such as constant variance, or homoscedasticity, and normal errors. However, real-world economic data rarely conforms to this ideal. We often encounter issues like volatility clustering in financial markets, where large changes are followed by large changes. Other common challenges include regime changes from policy shifts, binary outcomes like a recession, and data recorded at mixed frequencies, such as monthly inflation and quarterly GDP. This discrepancy, or estimation gap, means that standard OLS estimators can become biased or inefficient, leading to incorrect conclusions. Advanced methods are designed to specifically address these violations and restore rigor to our analysis. This chart serves as a crucial methodological navigator, emphasizing that the selection of an econometric model should always stem from a careful diagnosis of your data's unique characteristics, rather than memorizing methods. The core principle is clear: diagnose first. The inherent nature of your dependent variable and the error term will dictate the most appropriate method. For instance, if you're dealing with volatility and risk, especially in financial data, models like GARCH and GARCH are essential. If your focus is on long-run dynamics and equilibrium relationships between non-stationary variables, you'll turn to cointegration or ARDL models. When working with data collected at different frequencies, the MIDAS model offers an elegant solution. Should your dependent variable be non-continuous, such as a binary choice or count data, Logit, Probit, or Tobit models are the correct approach. For situations involving nonlinearities or structural breaks, consider thresholds or breakpoint models. Finally, to ensure robustness against outliers, methods like robust least squares or quantile regression are valuable. This systematic approach ensures your analysis is both accurate and meaningful. In finance, we often prioritize modeling variance and risk over the mean, a task perfectly suited for ARCH and GARCH models, which are crucial for value-at-risk analysis. This equation defines the conditional variance, HT. It comprises three parts: a constant omega, the ARCH term, alpha epsilon squared at t-1, representing news or shocks from the previous period that drive volatility clustering. The GARCH term, beta t-1, captures the persistence of volatility, indicating how much of yesterday's uncertainty carries forward. For stable volatility that eventually reverts to its long-run average, the sum of alpha and beta must be less than 1. Extensions like eGARCH and tGARCH allow for modeling asymmetry and threshold effects. These models effectively show how significant events can cause volatility to spike and then gradually subside, providing a robust framework for understanding market risk. This slide focuses on three powerful econometric approaches for analyzing time series dynamics: ARDL, cointegration, and MIDAS. The overarching goal of these methods, as highlighted in the trend versus cycle box, is to accurately separate long-run equilibrium relationships, or trends, from short-run deviations, or cycles, and to manage data collected at different frequencies. First, the autoregressive distributed lag, or ARDL, model is highly flexible as it can handle variables that are stationary, non-stationary, or a mix of both. It's particularly effective at distinguishing between immediate short-run shocks and the underlying long-run equilibrium that variables converge towards. Closely related are cointegrating regressions, such as FMOLS and DOLS, which are used when variables are non-stationary but have a stable long-run relationship. These methods are robust to endogeneity issues often present in non-stationary data. Finally, the mixed data sampling, or MIDAS model, addresses the challenge of mixed frequency data, allowing us to predict a low-frequency variable, like quarterly GDP, using high-frequency indicators, such as daily stock returns. This is achieved through sophisticated polynomial weighting schemes that give more relevance to recent high-frequency observations, offering a superior alternative to simple data aggregation. When the dependent variable, y, is not a continuous number, standard ordinary least squares is inappropriate. As the graph clearly shows, a linear probability model can predict nonsensical values, such as probabilities below 0 or above 1. Instead, models like Logit and Probit provide logical bounds, ensuring predictions stay within a valid range, such as probabilities between 0 and 1. We utilize specific models tailored for different types of limited and discrete dependent variables. For binary outcomes, like a yes or no decision, Logit or Probit models are used. For censored data, where we only observe outcomes above a certain threshold, such as non-negative purchases, the Tobit model is appropriate. And for count data, like the number of events, Poisson or negative binomial models are designed for non-negative integer outcomes. All these diverse models are often unified under the framework of Generalized Linear Models, or GLM. Take the example of a bank modeling a customer's loan default probability. Since default is a binary outcome, yes, no, a Probit model can accurately output a valid probability, like 5%, ensuring the prediction is both statistically sound and logically coherent. This class of models ensures our analysis respects the inherent nature of our data, leading to more reliable conclusions. Ordinary least squares, or OLS, primarily focuses on the average effect, as depicted by the peak of this distribution. However, in many economic and financial scenarios, the most insightful information lies in the tails, the extremes of the distribution. This is where quantile regression becomes invaluable. Instead of just modeling the mean, it allows us to analyze how an explanatory variable impacts different parts of the outcome variable's distribution, helping us understand tail risks or extreme outcomes. For instance, in an education income model, OLS gives the average return, but quantile regression can show a much larger impact on high-income individuals, 90th percentile, compared to low-income individuals, 10th percentile. Furthermore, economic relationships are not always static. Breakpoint tests are essential tools to identify structural changes or regime shifts where a coefficient, beta, changes over time due to policy changes or market events. When our data is contaminated with outliers, standard OLS estimates can be distorted. Robust least squares methods, like M-estimation, provide more reliable estimates by being less sensitive to these extreme observations. Lastly, for situations with many potential predictors, penalized regression techniques such as Lasso or Elastic Net help with variable selection by effectively shrinking the coefficients of less important variables to 0. This suite of methods collectively ensures a more comprehensive and robust analysis beyond simple averages. In EViews, accessing nearly all single equation models follows a universal path by going to Quick, and then selecting Estimate Equation. This action brings up the main estimation dialog box, which is our starting point. The real power and flexibility lie within the Method dropdown, which effectively acts as the command center for our econometric analysis. When you change this selection from, say, basic least squares to an arch, ARDL, or a binary choice model, the entire dialog box dynamically reconfigures itself. This ensures that the options presented perfectly align with the specific econometric theory you've chosen, guiding you towards the correct model specification and parameter inputs. This dynamic adaptation streamlines the process, allowing us to implement the advanced techniques we've discussed earlier, from capturing volatility with ARCH models to analyzing long-run dynamics with ARDL. In EViews, nearly all single equation models, including ARCH and ARDL, are estimated via the quick estimate equation path. The central control for configuring these models is the method dropdown, which dynamically adjusts the entire dialog box to fit your chosen econometric theory. Precision in these configurations is paramount, as specification truly matters for model validity. For ARDL models, accurately selecting the lag length is critical, and automatic selection criteria can help ensure an optimal choice. When working with ARCH models, the variance regressors box offers a powerful capability, allowing you to explicitly incorporate external factors to test what specific variables might be driving the volatility itself. This meticulous specification ensures that your model accurately reflects the underlying economic phenomena and produces reliable results. When performing advanced econometric analysis in EViews, configuring the estimation options correctly is critical for obtaining robust and reliable results. This slide highlights key settings available under the Options tab within the EViews estimation dialog. Firstly, regarding robustness, it's crucial not to overlook the Options tab. Selecting robust covariances, particularly the HAC, Nui-West method, is often necessary. This addresses potential autocorrelation or heteroskedasticity that may remain in the residuals, providing valid standard errors even when classical assumptions are violated, which we've discussed as common in real-world data. We also see options for optimization methods, like Newton-Raphson or BFGS, which are critical for ensuring the convergence of complex, nonlinear models. The estimation weighting matrix dropdown explicitly shows the HAC, Nui-West, selection for robust standard errors. Furthermore, for detecting structural shifts, we have the step method options, such as biparent, which are essential for identifying breakpoints in time series relationships. The screenshot also indicates the use of GMM, the generalized method of moments, a powerful estimation technique when dealing with endogeneity or conditional heteroskedasticity. These advanced options are not merely cosmetic. They are fundamental tools to ensure your model estimations are sound and your inferences are statistically valid. The principle of garbage in, garbage out is paramount in econometrics. The validity of your results depends on using a method that matches your data's properties. A unit root test, like the Phillips-Parent test shown here, is used to determine if a time series is stationary or non-stationary. The null hypothesis of these tests is that a unit root exists, meaning the series is non-stationary. We look at the probability value, or p-value, to make a decision. If the probability is less than 0.05, we reject the null and conclude the series is stationary, often denoted I0. If it's greater than 0.05, we cannot reject the null, and we treat the series as non-stationary, or I1. For instance, in the table, the series LNFDI has a probability of 0.0191, which is less than 0.05, indicating it is stationary. Conversely, LNGDP has a probability of 0.9206, so we conclude it is non-stationary. This critical pre-estimation step ensures we select the appropriate econometric model for reliable results. After conducting our pre-estimation tests, we move to step 2, executing the model. EViews provides two primary ways to do this, either through the command line, as you see with the equation EQ1 ARDL example, which is often more efficient for complex or repetitive tasks, or via the intuitive graphical user interface shown below. A crucial decision in model estimation, especially for models like ARDL, is determining the appropriate lag length. Here, we leverage automatic lag selection using criteria such as AIC or SIC. This is a powerful feature because it objectively removes human bias in model specification. By allowing the software to find the optimal lag structure, we ensure a robust balance between the model's ability to fit the data and its overall complexity. The interface also allows us to specify the error distribution, with normal Gaussian being a common choice. After successfully executing your model in EViews, the crucial next step is interpreting the output. As we see here, the key to understanding individual coefficient significance lies in the prob column. A probability value less than 0.05 indicates that the corresponding coefficient is statistically significant. In this GARCH model output, both the res-1 squared term, representing past shocks, and the GARCH -1 term, indicating volatility persistence, show p-values of 0.0000. This highly significant GARCH coefficient of 0.892 reveals that approximately 89% of yesterday's volatility carries over to today, confirming strong volatility clustering and persistence in our series. This aligns with the principle that in ARCH models, significant GARCH coefficients imply persistent volatility. We also observe overall model FID statistics, like the adjusted R-squared and the Durbin-Watson statistic, which provide a general sense of the model's explanatory power and residual autocorrelation. While not directly displayed here, it's also worth remembering that in ARDL models, a bounds test F statistic greater than the upper bound signals a long-run relationship. With these interpretations, we're ready for the final critical step, diagnostic testing. A model's usefulness hinges on its stability and proper specification, which we confirm through rigorous post-estimation diagnostics. The graph displays the conditional variance, where significant spikes, like those seen here, indicate that our model has successfully captured periods of heightened risk or volatility. This is a crucial validation for volatility models. We then perform critical tests. The serial correlation LM test is vital for checking if our model's residuals are truly white noise, meaning they are random and unpredictable, as they should be for a well-specified model. Furthermore, the Q-sum test, or cumulative sum test, is a powerful tool for assessing parameter stability over time. If the Q-sum line deviates and crosses the red significance bands, it serves as a strong indicator that the model's parameters may have shifted, signaling a structural break. Therefore, a model is only reliable if these diagnostic checks confirm its stability and that its parameters haven't unexpectedly shifted, ensuring the results are robust and trustworthy. To recap our journey through advanced single equation analysis, this matrix summarizes the key econometric problems we often face and their appropriate solutions. When dealing with volatility risk in financial data, ARCH and GARCH models are your essential tools. For uncovering long-run equilibrium relationships among time series, even if they are non-stationary, cointegration and ARDL models provide robust frameworks. If your data involves mixed frequencies, such as daily and quarterly observations, the MIDAS model offers an elegant solution to integrate them effectively. For qualitative or binary dependent variables, like predicting a yes-no outcome, Logit and Probit models are the correct choices. Finally, to address outliers